Today we're going to look at stratospheric ozone depletion, both causes and effects of this very important portion of our atmosphere. So we'll be able to differentiate between tropospheric and stratospheric ozone, look at reactions for formation and depletion of stratospheric ozone, identify the ozone depleting compounds, look at the relationship between stratospheric ozone concentrations and time of year where the thinning is most pronounced, impacts on both plant and animal populations, and also identify the global agreements that have been used to mitigate the impacts and to try to reverse the trend that we see in the decline of stratospheric ozone. So, some ozone factoids. Remember our mantra, good in the stratosphere, bad in the troposphere. Troposphere or stratospheric ozone is produced at a height of about 50 kilometers toward the top of the stratosphere, but it settles out to a height of about 23 kilometers. It filters out approximately 95% of the incoming UVB and UVC radiation. It doesn't really potentially filters out maybe 50% of the UVA. When we look at the mechanisms for the formation of stratospheric ozone, it does somewhat explain the warming trend in the stratosphere. Remember that according to the law of conservation of energy, energy is not created or destroyed, but it can be converted from one type to another. And in the stratosphere, we see ultraviolet energy being used in reactions and being released as infrared radiation. Ozone depletion is a global problem. When we look at problems like photochemical smog or industrial smog, those tend to be local problems. Acid deposition tends to be a regional problem, and ozone depletion, stratospheric ozone depletion, is a global problem, and it is a problem that has been successfully or started to be successfully addressed. So where do we find ozone in the atmosphere? As I mentioned earlier, it actually forms at about a height of 50 kilometers, but you can see that the thickest portion of that layer is found in the stratosphere at a height of about 23 kilometers. And that protective layer, again, is very important for us. So how does the ozone form? Well, in the stratosphere, UVC radiation breaks apart an oxygen molecule into oxygen atoms. These are actually free radicals. They have an electron that's unpaired. And free radicals are very reactive chemical species. They're essentially self-catalyzing species when you're looking at chemical reactions. So what happens to that oxygen free radical? Well, it can react with an oxygen molecule and produce ozone. Oxygen free radicals can react with each other to produce oxygen molecules. Ozone can react with UVB or UVC and produce an oxygen molecule and an oxygen free radical, and that reaction can begin to occur again. If you're looking at the kinetics of what goes on, the fast step is going to be the formation of ozone. If not, we would never get a buildup of that layer in the atmosphere. And you can see the different wavelengths for UVB, UVC, and UVA. And again, it's UVB and UVC that are essentially utilized in these reactions. So why do we have depletion of stratospheric ozone? The major culprit are freons, or CFCs, or chlorofluorocarbons. And as we'll see in a minute, a freon molecule can be responsible for the destruction of 100,000 ozone molecules because of the chain reaction that is set up. So what are freons? When did they come into play? And why are they such a problem? Well, freons first came into play in the 1930s. And they were introduced by Thomas Midgley. In fact, he demonstrated that they were relatively non-toxic species by taking a big hit of the freons and then blowing out a candle. Mr. Midgley was also responsible not only for freons, but also introducing lead into gasoline as a anti-knocking agent. So freons were non-toxic, essentially non-reactive in the troposphere. What were they going to be used for? They were going to be used for replacements of things like ammonia that had been used as a refrigerant. And you know that if you inhale ammonia, ammonia is toxic. Freons, on the other hand, were not toxic. So where were they used? They were used as refrigerants. They were used as the propellant in spray cans and aerosols. They were used as the blowing agent to produce things like styrofoam. They were used as cleaning solvents for printed circuit boards because of the fact that they were inert. Methyl bromide. Methyl bromide is a fumigant used in agriculture. So it's a soil fumigant. Halons were used in fire extinguishers. High-flying jets released nitrogen oxides into the stratosphere. And probably one of the newer threats that we're becoming aware of is nitrous oxide, N2O. And that's produced as from the decomposition of fertilizers and also from manure in CAFOs. So let's take a look and see how a freon molecule, and this is just one example of a freon molecule, can lead to the destruction of the ozone layer. So in this diagram, you have a typical freon compound, CFC12, used for air conditioners, car air conditioners, home air conditioners, refrigerators. And in the stratosphere, when this compound finally makes it up there, and remember, these compounds remain stable in the troposphere for 30 or 40 years. So we started using them in the 1930s and 1940s, and we didn't notice a problem with stratospheric ozone until the 1970s and 1980s. UV light hits the molecule, it cleaves off a chlorine atom. That chlorine atom, chlorine free radical, can react with ozone to produce oxygen and chlorine monoxide. The chlorine monoxide can react with ozone to produce oxygen and the chlorine free radical. And the chlorine free radical can go back and begin destroying ozone molecules. So again, this process and one CFC molecule can destroy upwards of 100,000 ozone molecules. So how do nitrogen compounds have an impact on stratospheric ozone? Well, nitrous oxide, if it makes it up, can react with one of those oxygen-free radicals and produce nitrogen monoxide. NO can react with ozone to produce NO2 and oxygen. NO2 can react with a free radical to produce NO2. NO2, or nitrogen dioxide, from fuel combustion in high-flying jets can also react with those oxygen-free radicals. When you look at all of these reactions, your net result is that ozone is being destroyed and oxygen is being produced in the process, hence leading to that thinning of the layer that we see. So the thinning was most pronounced over Antarctica. Antarctica is one of the coldest places on the planet. And when you think about how the Earth is shaped, we're not a perfect sphere. We're not perfectly round. And so the height of the atmosphere, the troposphere, is a little bit lower in the polar regions. And because of that, you do get some water vapor and you can produce polar stratospheric clouds, all part of this large polar vortex that moves through the area. Those clouds and the surface of those clouds provide a way to hold in those chlorine atoms during the wintertime. It's dark, it's cold. Those atoms and those chlorine compounds can be held in those ice crystals. When springtime comes in the Antarctic, those ice crystals melt, they release those chlorine atoms, and those chlorine atoms can go back to work destroying stratospheric ozone. Originally, the most pronounced thinning was seen over Antarctica, and that obviously posed massive concerns. But likewise, as we hit into the 80s and into the 90s, we started seeing a thinning, not as great, but occurring over the Arctic. And part of the issue that ties into that is that human populations are much greater in the northern hemisphere than they are in the southern hemisphere. So how do we measure this? How do we know what goes on with this thickness, and when did they start looking at it? So there's a gentleman named Mr. Dobson, and he developed a device to measure the thickness of these layers. We talk about Dobson units, we talk about TOMS imaging. What exactly is this Dobson unit, and how can we make this more real for you? Well, a Dobson unit is defined as zero point zero 0.01 millimeters thickness at standard temperature and pressure. So if you compress this column of air, you'd get this thickness. The average thickness of the stratospheric ozone is about 300 Dobson units. The hole that was seen in the mid-1980s dropped to about 100 Dobson units. To give you an idea of what that thickness really relates to, 300 Dobson units is about the thickness of 2 pennies if you stack them up, whereas 100 Dobson units is equivalent to the approximate thickness of a diamond. Before 1979, we had never seen ozone drop to a layer below 220 Dobson units. This is an example of a TOMS image and the kinds of image they get as they are looking at Antarctic, and they can also look at the Arctic thickness of the ozone layer. The deeper the color, the deeper the purples, the thinner the layer. And you can go online and you can look at images. I'll provide you a link to look at images throughout the year, and you can see how this thickness, if you will, changes with respect to seasons. Ozone Watch from NASA has images that go back more than 10 to 15 years, and you can look at how the layer has changed. Just to give you an example of the change in the thickness or the size of the ozone hole, remember it's not only the thickness, it's the area that this thinning encompasses. And you can see fairly steadily since the 1980s, we've seen an increase in the size of the ozone hole, and that poses problems with respect to all living organisms. So what are the impacts? Well, for every 1% decline in the ozone layer, and you can imagine how thin that is, can represent a 4 to 5% increase in the rates of skin cancer. That includes increases in the rates of melanoma. Think about it. Every time you go out now, people tell you to put on sunscreen. Think about it. Most glasses, sunglasses or regular glasses, even contact lenses, tell you that you're protected against UVB and UVC radiation. And that's because that increase in ultraviolet energy reaching the Earth is responsible for cataracts, both in humans and in wildlife. Think about people that have pets, for your dogs. Think about how many dogs get cataracts now. And, I don't think people really thought about that before. It can impair and your immune system, make you more susceptible to disease. Because of the fact that it impacts photosynthesis, we get a decline in phytoplankton population. There's been a 6 to 10% decline in the phytoplankton population in the Antarctic regions. What does that do? That impacts food chains and food webs. So if you don't have phytoplankton, you don't have zooplankton, you don't have organisms like krill, and what are things like baleen whales and squid going to eat if there is no krill? And those kinds of declines in phytoplankton can have impacts all the way up the food chain, impacting both fisheries and food that you can eat, harvest, and eat. It impacts crop yields because it impacts photosynthesis, forest productivity. And when you think about it, the increased ultraviolet light reaching those regions, especially in the Arctic and the Antarctic, may be outside of the range of tolerance for some aquatic species. Remember that it was the formation of stratospheric ozone, oxygen and then stratospheric ozone, that really allowed life to make that big jump from the oceans onto the land surface. And lastly, CFCs or freons are also a very potent greenhouse gas in the troposphere. However, just because CFCs are a greenhouse gas in the troposphere does not mean, and let me emphasize that, does not mean that stratospheric ozone depletion is the reason for climate change or global warming. So what are our solutions? Well, our solutions are ban CFCs. And as we phase those out, and we'll look at the global agreements, some of their replacements also pose problems. Ban halons, ban methyl bromide. It wasn't until the 1970s that we really began to look at the role that CFCs could play in the destruction of stratospheric ozone. And two of the scientists that played a very large role in that are Sherwood Rowland and Mario Molina. They did a lot of work in the 1970s to look at the reaction mechanisms that would lead to the destruction of stratospheric ozone. In fact, in 1995, they won a Nobel Prize in Chemistry for looking at the reactions that caused that decline in stratospheric ozone. So their work in the early 1970s led to banning freons as propellants in spray cans in the United States in 1978. So it did have a positive impact. It did have a positive impact. The first time we really saw that major thinning was in 1985, and that's when the world sort of freaked out and thought, oh my God, the ozone layer is disappearing. And that led to one of the major global agreements in 1987 of the Montreal Protocol. One of the reasons we also want to find replacements for, and we'll talk a little bit more about the protocol in a moment, one of the reasons why we want to find replacements for HFCs or for CFCs and also HFCs, their replacements, is because although HFCs don't make it up to the stratosphere as quickly, HFCs are also very potent greenhouse gases. We have managed to find replacements for halons in fire extinguishers and still working on globally banning methyl bromide. So in 1987, we had the Montreal Protocol. And the Montreal Protocol looked at phasing out all freon compounds. Again, the Montreal Protocol was looking at phasing out all CFCs by the year 2000. That protocol, that global agreement, and it's a global agreement that's actually worked, was amended in 1990. It was amended in 1992 to include compounds like methyl bromide. And it's continually been amended and looked at. As of 1996, 96 ozone depleting compounds had been looked at and had been given a schedule for being phased out. So what's the upshot? The upshot is if we continue to phase out these compounds, if we get a handle on nitrous oxide, then the ozone layer may actually recover to its pre-1970 levels by the year 2050 or 2060. You know, many times we feel that global agreements don't work, and we've seen the difficulties that we've had to get global agreements in play with respect to climate change and greenhouse gases. But we've been very successful with these agreements to phase out these ozone depleting compounds. Again, the newest threat really identified in the early 1990s is nitrous oxide. And one of the reasons why this poses such a threat is that there's not a way that you can ban fertilizer or ban manure. There's certainly ways that you can lessen those impacts, but it does continue to be a threat, and nitrous oxide is also a very potent greenhouse gas. I hope that explained a little bit to you today about stratospheric ozone depletion, the reactions that cause it, and ways that we are trying to correct this issue.